The overall goal of this procedure is to control complex patterns of light in time and space so that it can be used to stimulate neurons. This is accomplished by first positioning a DMD chip at an appropriate conjugate image plane in the optical path of the microscope. The second step of the procedure is to properly illuminate the DMD with an intense light source, such as a laser. The third step of the procedure is to eliminate the speckling effect of coherent illumination. The final step of the procedure is to integrate a graphic user interface to manipulate the DMD chip. Ultimately, results can be obtained that show experiments that were previously difficult to accomplish can now be completed relatively easily through multi-site photolysis of caged neurotransmitter employing the DMD system.
Hi, I'm Michael Mohammadi in the laboratory of Dr. Tang at the University of Maryland, Department of Neurology. Today we will show you a procedure for generating complex patterns of illumination in an optical microscope. We use this procedure in our lab to study dendritic integration, so let's get started.
This protocol will demonstrate the operation of a digital micromirror device, or DMD, illumination system for experimental neuroscience. A DMD is an optical semiconductor chip with several 100,000 microscopic movable mirrors arranged in a rectangular array on its surface. The position of each mirror corresponds to the pixel of an image. Each mirror can be individually controlled to tilt between two orientations. In the off orientation, the light is directed away from the optical axis of specimen illumination. In the on orientation, the light is directed along the optical axis. DMD is well suited for photolysis.